Welcome back to our series where we're setting up our PM-1340GT. We've got the machine out of the crate and on the stand, all the surface preservative is cleaned off, and we're just about ready to make chips. One last thing that we need to do before we can make precision parts on this lathe is to make sure the bed is completely straight with no twist. Some people like to do that by moving the machinist level down the ways and making tiny adjustments to the leveling feet until the bubble is in the middle all the way down. I mentioned in the last video how that's not my preferred method, so I'm going to show you how I like to do it. Let's get started. Even having leveled the lathe in the previous video, chances are the ways are still not sitting absolutely straight. Rather than go further with the machinist level, we'll cut a test bar, which allows us to intuit which direction the ways may be twisting. Note the shape of the test bar. Some people call this a barbell shape with a journal on each end and a relief cut in the center. That relief cut is just a time saver so that we can go from one journal to the other without having to cut the entire length of the bar. Absolute dimensions of the bar don't matter, we're just measuring the difference in diameter of these two journals. So we dial in a light cut, lock the cross slide, start the feed, we'll cut the first journal, then disengage the feed, move over to the other end of the bar and cut that second journal. I like to feed away from the chuck, so that you can start quite close to the chuck and get the maximum sample length for your test bar without risking a crash. Now let's see how close we are before we even place our first shim. Using an outside micrometer, we'll simply measure the diameter of each journal. Again, the absolute measurements don't matter, so whatever size material you have is fine. It just needs to be long enough that you can get a couple inches between journals and thick enough that you can cut it without tail support, as we're taking the tailstock completely out of the equation here. We made our test bar out of about a 6-inch piece of 1.5-inch aluminum round because that's what we had, but steel works fine too. The journals on our test bar ended up being about 4¼ inches apart, and that's enough to detect any twist. I like to write my measurements in the relief cut on the workpiece itself with a Sharpie, then mark the large side with the difference in diameter. If you write it on a piece of scratch paper, you can get turned around and forget which side is which. Or, I don't know, maybe you're smarter than me and it's not a problem for you. But I like to use the idiot-proof method. Let's not think too hard about what that says about my status as an idiot. So in my case, before I place any shims, the end toward the tailstock is 1.3 thou larger than the end toward the headstock. So the question that even an idiot would ask is, what do we do with that information? It's sometimes hard to imagine something that seems rigid twisting a significant amount, but tell that to the designer of the Tacoma Narrows Bridge. So let's imagine that the ways on our machine are so twisted that when I try to turn a cylinder, I actually get a cone like this, with the fat part toward the chuck and the skinny part toward the tailstock. What does that tell us about the movement of the tool? It tells us that the tool is moving in toward the work as it goes toward the tailstock. That means the tailstock end of the ways is twisted clockwise in relation to the headstock. So we'll call on machine tool Sisyphus to push in the opposite direction. Now our friend Sisyphus has a lot on his plate just with his rock, so we should use some shims instead. The shims placed here will twist the tailstock end of the lathe in the opposite direction of the error. Wait, are the shims more like Sisyphus or Atlas? Well, we already made the graphic, and this metaphor is getting away from me, but I think you get it. But remember that our test bar has the big end toward the tailstock, like this. So that means that we're twisted the other way, and the tool is moving away from the workpiece as we go down the ways. So we need to twist it this way, and place our shims here. If you want, you can ignore all that explanation and just remember the rule. If the big end of the bar is toward the headstock, shim in the back. If the big end of the bar is toward the tailstock, shim in the front. Okay, we know where the shims are going, but how do we know what thickness of shims that we need? This equation gives us a good starting point. Since the test bar is essentially a sample of the twist in one section of the ways, we can extrapolate that out to the full length of the lathe bed. That means that the difference in journal diameter divided by the distance between journals is going to be roughly equal to the shim thickness divided by the total bed length. We can cast our minds back to middle school algebra to isolate the shim variable on one side of the equation, and we get shim thickness equals bed length times journal diameter over length between journals. For our example, we have 1.3 thou of difference, over 4¼ inches equals X shim thickness over a 40-inch bed length. 1.3 over 4.25 times 40 gives us just over 12, so we'll start with a 12 thou shim. We'll cut, test, and adjust shim thickness as many times as we need, so this is just a rough estimate, but it gets us in the ballpark. You might still have the engine hoist out from when you placed the lathe on the stand, so use that to pick up the tailstock end of the lathe. I've loosened the bolts and I'm picking the machine up just enough to slide the shims in. If you don't have the fancy U-shaped shims, it's okay to cut a piece of shim stock in half and put one piece on either side of the bolt. Just be careful cutting that shim stock, and notice there's a band-aid on my finger in this shot that wasn't there in previous shots. Enough said about that. Now we just cut again, measure again, and adjust the thickness of our shims if needed. After placing that 12 thou shim in the front, we went from 1.3 thou bigger toward the tailstock to 0.2 thou, or 2/10 bigger toward the headstock, which means we went just a little too far. I replaced the 12 thou shim with an 11 thou shim, and that got us very close, just 1/10 bigger toward the tailstock. 1/10 over 4 inches is acceptable in just about any application, but even if you're into chasing zeros, you still want to leave it alone for now, knowing that it could move from there as the castings relax into position. We can test it in a month or two and possibly adjust the shims then. It shouldn't move much, but it could move a couple of tenths. While we're aligning things, let's take a look at the tailstock. The quickest way to check that is with a razor blade held between centers. This machine came from the factory just about dead on, but we moved it 10 thou out so you can see what that looks like on the razor blade. You'll just use the screws on either side of the tailstock to push it one way or the other. This is what it should look like when you're done. There might be minor parallax effect to this shot, but in person you can look straight down from the top and see the difference between perfectly straight and out as little as 1 thou. So this method is quite accurate. So there you have it. The bed of the lathe along with the tailstock are aligned with the spindle of the machine. You can now turn cylindrical parts with as little taper as possible, and your tailstock will hold the end of longer parts directly on center. If you think I missed anything about this process, let me know in the comments below. I always like to hear how other people level their machines, and maybe I can learn something. Thanks for watching.